This is College Algebra, Chapter 2, Section 4, where we're going to talk about more on slope. And the first subtopic, as we talk more about slope, is parallel and perpendicular lines. And I've gone in and highlighted some key features of these notes. Now, if you're one of my students in College Algebra, then you have access to these notes in my math lab in the left-hand column under Notes. And the first thing I wanted to point out that I've pre-highlighted for you is that non-vertical lines are parallel if they have the same slope. And if you have two vertical lines, it's tough to say that they have the same slope because they have undefined slopes. So if you have two lines with both of which have an undefined slope, then those lines are parallel also. If you have perpendicular lines, those two lines, if neither one of them is vertical, then the product of the slope of those two lines will equal -1. Another way to say that is that perpendicular lines have slopes which are opposite reciprocals. For example, if the slope of your first line, m1, is equal to 2/3, then the slope of the perpendicular line, m2, will equal the opposite reciprocal, which would be -3/2. So you see that the fraction has flipped and the signs are opposite. And indeed, if you multiply those two fractions together, you'll get -6/6, which reduces or simplifies to -1. Similarly, if you have a line with a slope of 7, or -7, let's say, then the slope of the perpendicular line will be +1/7. And again, in that case, if you multiply those two slopes together, you would also get a product of -1. If one of your lines is horizontal and one of your lines is perpendicular, then those two lines would also be perpendicular. So a horizontal and a vertical line with a slope of 0 and an undefined slope for the vertical line, those two lines don't so much have a product, or don't so much have a product of slopes that's equal to -1, because multiplying by undefined would be strange. So just realize that if you have a horizontal and a vertical line, then those two lines are going to meet at a right angle, which means that they are perpendicular. And then I want to look at some example problems with you, and I'm not going to go into detail with all of these problems because once you know how to set them up, you should be able to piece together the different processes involved in a couple problems in order to answer all of these types of problems. So let's look at this first one. We are going to use the given conditions to write an equation for a line in point slope and slope intercept form, where the line passes through the point -2, -7, and is parallel to the line whose equation is y equals -5x plus 4. Now the instructions here are telling us to write our equation in point slope and slope intercept form, so let's just refresh our memory. Point slope form is y minus y1 equals m times x minus x1, where y1 and x1 are the coordinates, or I should say x1 and y1, are the coordinates of the point that's being given to you. In this case, that's -2, -7. And m represents the slope. We're not going to plug in anything into y or x. Those are going to remain so that we end up with an equation that looks like this, that still has the variables y and x available to be variables. The other slope intercept form that we need to know is the one that we know so well, y equals mx plus b. We will need a slope value there for example, -5, and we will need a b value, for example, +4, unless the b value happens to be 0, in which case we won't have a b value written. So let's try this one. Because we're being given a point, I'm immediately tempted to use point-slope form, and we're told that the line that we're writing an equation for is parallel to this given line. And this line has a slope of -5, so our new slope is also going to be -5 because our new line will be parallel to this one, so they'll have same slope. Let's take the given information now, the point that we were given, and the slope that we were sort of covertly given, and plug those into point-slope form. So we have y minus our y1 value, which is -7, and I put it in parentheses just to make sure that we account for the double negative as we clean it up, is equal to, our slope is -5 times x minus our x1 value, which is -2. And then we'll clean this up and present that as the first part of our answer. Y plus 7 equals -5 times the quantity, x plus 2. So this is our answer again in point-slope form. And then we're going to manipulate this equation so that it says y equals, and we'll set up the format on the right-hand side to match up with mx plus b. First, on the right-hand side of the equation, let's distribute the multiplication by -5. So I'll put a little note here, dist for distribute. Nothing's changing yet on the left-hand side, but on the right-hand side we have -5x minus 10. And then we'll subtract 7 from both sides to get that y isolated on the left-hand side. And on the right-hand side, we didn't modify the 5x. We're only subtracting a constant value of 7 from both sides. So our b value turns out to be -17. And that is your answer in slope-intercept form. So the sort of processes that we need to be able to take forward with us are knowledge of the two different forms for the slope of a line, and often we're going to be starting with point-slope form, which is this first one that I mentioned. We need to have the ability to extract the necessary information to plug it into point-slope form. Now, sometimes you're going to be given 2 points. Sometimes you'll only be given 1. It doesn't matter which of those 2 points you use. And if this problem had been different, instead of it saying parallel, if it had said perpendicular, then we would not be using a slope of -5. We would use the opposite reciprocal, and our slope would have been positive 1/5. And we would have used the same x1, y1 of -2, -7. So using the same point but plugging in a different slope, that would have happened here, and then the rest of these processes would have been the same. So just the initial setup of your point-slope form equation would have changed, and then everything else would have been the same. Let's see what happens in this next example. We want to be passing through a point, so there's your x1, y1 values, x1, y1. Take note that our new equation is going to be perpendicular to the given equation, which means that their slopes will be opposite reciprocals. And now we need to extract the slope from the given information here. It's a little bit more hidden than it was in the previous problem. We need to take this given equation and put it into y equals mx plus b form so that it's easy for us to extract the slope. So let's isolate y on the left-hand side. The first thing I'll do is add 12 to both sides. And then we'll subtract x from both sides. So I'm just leaving that 7y where it is. And you'll notice that I put the minus x to the left of the 12, which is okay. The x is still negative on the right-hand side, and the 12 has remained positive on the right-hand side. The order of those two things can be switched around. That's called the commutative property of addition or subtraction. They abide by the same rules. And then we're going to divide both sides of our equation by 7. We could have also multiplied both sides of our equation by 1/7. And maybe, let's do that. Division by a number, like dividing by 7, is equivalent to multiplying by the reciprocal of 7. So I'm going to multiply both sides by 1/7, and let's write that in. 1/7 times the existing 7y equals 1/7 times the existing entire right-hand side. And then we have to distribute. So I'll put a little note over here. DIST for distribute. The 7s are going to cancel on the left-hand side, which is what we wanted to happen. We wanted to isolate our y value. And then we'll distribute that 1/7 on the right-hand side. So notice that the first term became a negative 1/7 x, so that the negative that was there has come along with us, and the x has come along, and the multiple of 1/7. Their order changed around a little bit, which is okay. That is the commutative property of multiplication. So because this is all multiplication right here, those elements could move around. It would be strange to put the negative sign in the middle because it would look like subtraction, so we bring it out front. And the reason that we did all of that was to discover that the slope of the line that they gave us is negative 1/7. And remember that the equation for the line that we are creating is going to be perpendicular to the line that was given to us, which means that our new slope is going to be the opposite reciprocal of negative 1/7. So let's put a little note here. Given slope of negative 1/7, so perpendicular slope will be simply positive 7. And now we have all the information that we need. You don't really need me to go forward with this problem. You have your point, you have your slope, and you're going to plug those into point slope form, just like we did in the previous equation, or in the previous example. I'll still work through it with you, but I want to drive home the point that there are only select little maneuvers involved in solving these problems, and if you can isolate those little maneuvers as separate tools that you need to solve these problems, just realize that you have to mix and match them and maybe put them happening in a different order in order to answer these questions correctly. Alright, so let's keep going and plug in our given information. We have y minus y1 equals m times x minus x1. Let's plug in our information. Y minus our y value of negative 9, so be careful with the double negative there. The slope of our new line is positive 7 times the quantity x minus our x1 value, which is positive 5. I didn't really need to put the positive 5 in parentheses. Having the negative 9 in parentheses is my way of reminding myself to deal with this double negative that's happening over here. But not really necessary for the 5. It's just kind of a habit that I usually do that. So let's simplify this or clean it up a little bit. We'll write it as y plus 9 equals 7 times x minus 5. And that's our final answer in point slope form. And then we'll do the exact same couple of maneuvers that we did in the previous example. We're going to distribute. Nothing's changing on the left-hand side, only distributing on the right-hand side. And then we'll isolate our y value on the left by subtracting 9 from both sides. There's the y all alone. We're not modifying our x to the first term. And then we need 35 minus 9, which is negative 44. That's y equals mx plus b form, or slope-intercept form. And that's it. A related topic when we're talking about slope is called the average rate of change. And the average rate of change for a function is not an evaluation of the entire function. We don't find the average rate of change for the whole function. We find the average rate of change between 2 points on the function, on the line, on the curve, whatever the graph is. So average rate of change is synonymous with the slope of the line containing 2 points. And when you look at a graph like this one, and you pick 2 points on the graph, here and here for example, and you draw a line between those 2 points, we call it a secant line. And a secant line is a line that crosses your graph at more than 1 point. All right? If I had a point up here and I drew a line that just barely skimmed through that 1 point, that would be called a tangent line. So if it's not a tangent line, we're going to be working with a secant line. And we find the slope of a secant line using our traditional slope formula, which is at the top of your screen here. I would go so far as to write in m equals, because this is how we calculate slope. And this is the exact same thing as doing y2 minus y1 over x2 minus x1. We're seeing it written as f of x2 and f of x1 for a particular reason, and I'll show you what that is in this example. So from the printable notes that I'm using in order to describe these processes to you, the original function in this problem was 6x, and our x1 value was a 0. And I've modified it to be a second degree polynomial function. It's a parabola, and it is now f of x equals 3x squared. And we'll be going between points that have an x-coordinate of 1 and an x-coordinate of 4. So these are the x values that we're going to use to find the slope of our secant line. In other words, our average rate of change between 2 points. Well, where are the points? Well, the points are these 2 points that have x-coordinates of 1 and 4. Well, that's great, but how am I supposed to figure out the slope if I don't know my y values? And the answer is you need to take the x values and plug them into your function one at a time, and that will generate your y values for you. Well, then it's a good thing that they gave us a function to work with. So we're going to plug our x values into here in order to calculate y1 and y2. So let's say that y1 equals f of x1, and we know what x1 is. It's a 1. So we're going to take the 1 and plug it into our function. That's 3 times our x value of 1 squared, which is equal to 3. So our first point that we would be looking at specifically on our graph would be the point 1, 3. That is x1, y1. Let's go through the same process to find y2. y2 equals f of x2, which is equal to f of 4, which is equal to 3 times 4 squared. So take the 4, square it, get 16, multiply that by 3, and get 48, which means our next point that we're working with is 4, 48. That is x2, y2. Now it's very easy to find the slope of the secant line, the line that passes through these 2 points. Our average rate of change, in other words, our slope. If my pencil will work. Is it possible that my pencil has died? Anything's possible. I'm not getting a reading from my pencil. Maybe it's sleeping. It's sleeping. All right. And it's not letting me write with my finger. That's not very nice. Maybe don't need to do a signature. Right, so I'm going to pause. I'll be right back once my pencil has charged. All right, we're back in action. And we're calculating the slope finally. Let's do y2 minus y1 using that notation, or f of x2 minus f of x1 over x2 minus x1. Our y2 value is 48. Our y1 value is a 3 over 4 minus 1. And that gives us 45 in the numerator, 3 in the denominator, and that is reducible to 15. So 15 would be our average rate of change. And remember, that's an average rate of change for our function only on this interval that goes from an x value of 1 to an x value of 4. If we drew a rough sketch of our parabola, it will pass through the origin. It's a fairly narrow parabola because of that leading coefficient of 3. And at 1, we would have a y value of 3. And at 2, 3, 4, we would be way up here at a y value of 48. And I'm going to cheat and just throw a little straight edge on here. With how steep that line is, not as much of a surprise now that it does indeed have a slope of 15. And that is our last topic for this section. So I will bid you adieu until I see you for our next meeting. Thanks so much.